Start. So, hello everyone. So, we're going to discuss today about the three-dimensional viewing and the concepts, the basics, the introduction, how we are going to do everyone. And this is Darshan Gumadi from Team Hamilton.
చెప్పురా
These are our team contributions. So, I'll be explaining about the 3D concept and rest of my teammates, as mentioned, they're going to explain about this topic. Yeah. So, starting with the three-dimensional concepts, considering a 3D, a model, a 3D scene, considering each object in a scene, each one with their set of surfaces, which forms a closed boundary around the interior of the object. It means for some objects, we need to specify the interior of the object, and there are several graphic packages to do the tasks. And the function used to view, process the object descriptions that ultimately project a specified view of the project objects onto the surface of the display device. So we do encounter many common procedures between the both 2D and 3D viewing. And clipping routine is one of the such process. And about clipping routine, we are going to discuss it moving forward. And there are some additional tasks that are performed in 3D viewing, unlike 2D viewing, which is not necessary. So those are projection routines, surface characteristics, and lighting effects. Okay, viewing a 3D scene setup. We have been capturing with our phone camera lately. So whatever we are trying to view a scene in a position, we are capturing in a 2D way, and so that is called a reference frame. So when you set up a reference frame, setting up a coordinate reference for viewing the parameters, which defines the position, orientation of the view plane, then we need to transfer those objects to view the reference coordinates and project them onto the plane where you can see the view plane. Generating a view of object onto the output device in a wireframe form, we can apply the lighting effects and surface rendering techniques to realistic shading of the visible surfaces. And we can see in the picture, just like that, if you place a camera and you can, if a cone is placed in front of a camera, all you can see is a triangle from one angle because it's a 2D view. And the coordinate reference, whatever we are trying to showcase, will show only that particular shape from one point of angle view. So
okay, good question before we move on. Let's go back to that picture. Muted me. Can we go back? There we go. Now it shows that that one, yeah. That the question was, why is it that we use a plane instead of other surface? Was there any historical reasons why people use the plane, and then eventually we just copied it and created a plane like the display that I'm looking at? Or is this just a matter of convenience? Why plane and why not other kind of surfaces?
Okay.
What do you think?
So it's like both planes and surfaces serve the specific purpose based on the requirements. So why we use plane is because of its simplicity, efficiency, limited representation, and limited realism. So a plane is like simple geometric shape in 3D, defined by some few parameters, or it's easy to define or manipulate. Rendering a plane is like computational efficient, like it is like computationally efficient to render a plane instead of a surface. Yeah, it's like ideal for the applications, especially when dealing with like large flat surfaces like floors, walls, or backgrounds.
Yeah, it's certainly true. For computationally, plane is efficient, but our system that we use to record images, like the back of our eyes, that's not planar, right? That's more like spherical or close to spherical.
Yeah, I think limitations are there with the plane for like limited representation, with limiting the kind of structures or objects that can be accurately represented by just planes.
Right.
It's like
Well,
plane has only one surface.
right. Well, there is no simpler surface that's plane, that's for sure. And so you're right, simplicity is king. And well, the pictures that we've been generating are actually fairly reasonable. But I just wondered if you created images that were projected on a non-planar surface, would that be more visually appealing? Because we are just used to that.
Oh, okay.
Right. Just some question. Okay, let's move on.
Okay. So talking about like the scene setup, whatever we have seen here, and let's talk about the projections. How does they work? Like, a projection is something like which is image that is being transformed from a point in a high dimensional space to the low dimensional space. Uh, uh, there are like mainly like two basic methods in the projection. One is like a parallel projection, and one is a perspective projection. Let's discuss about the parallel projection. You can see in a figure 1. Let's imagine a solid object is being projected from a higher coordinate plane, like higher dimensional space, to the lower dimensional space. Even if it is a solid 3D object, the projection will just approach as uh, if it is a rectangular box, it just appears as a simple rectangular a shape. So that is called parallel projection. And moreover, the perspective projection, it's like perspective projection. Perspective projection is like a perspective projection, more realistic way, a view of like 3D scene by projecting points along the view plane, along the converging paths. It is called perspective because objects from the farther position going to be seen as a very smaller than the objects that are very nearer. So that is represented as like a perspective projection. Here you can see in the image how the image is getting smaller when the perspective is changed. The view from when you look at from the viewpoint. Yeah, and here we can discuss about the many softwares what we are going to use in a 3D viewing ways. We are very familiar with the Blender and Maya, and there are few other softwares which are like AutoCAD and Cinema 4D in the market. And last semester, we did use in the same in one more course to create 3D models using Blender. And this is the Maya 3D, which is used mostly they are using in the graphics movies and all such. So here we can see an image of car which is being modeled in 3D using the Maya software. And yeah, this is the one which I made last semester for an NFL and for designing an NFL helmet in a Blender. A Blender is one such software which allows you to make a 3D images with a very good rendering and look. So these are like very helpful tools where you can put your imagination into the picture. And let's talk about the wireframes. The most basic visual representation of like 3D, 3-dimensional physical object are seen under its using its underlying structure. It is called wireframe. It is essentially a skeletal outline that defines the shape, structure of the 3D model without incorporating surface or texture details. No surface detail. It's like simplified representation focusing solely on the object's geometry. Wireframe, like its purpose in 3D modeling is like no surface detail. Unlike other rendering techniques, a wireframe does not include any surface details, colors, textures, or lighting effects. It's a simple representation, again, like just solely just with the geometry. And visualization tools. Wireframe like serve as a visualization tool during the early stages of 3D modeling. They help the designers and artists plan the model's layout and proportions before adding finer details. And editing and modifications, wireframe are highly useful for making precise modifications to the model's geometry. Designers can easily manipulate and adjust the wireframes to redefine a 3D object. Efficiency and performance, coming into that part, displaying a wireframe is computationally less intensive compared to rendering a fully detailed 3D model. Fully detailed 3D model. Again, this makes it efficient. This makes it efficient in a real-time application such as 3D modeling software or video games. So wireframes are essentially a part of 3D modeling workflow, aiding in creation of like visualizations, fine-tuning, or intricate 3D models. They provide the fundamental structure upon which artists and designers build adding surfaces, textures, and other details to achieve visually realistic, appealing final rendering. So here are a few examples of wireframe. Here you can see a staircase, how it is being plotted. And this is just a image where you capture a city view and how the wireframe can be applied to that particular scene. So
you
there are
think
few,
that let's go back to that picture. Can we step back one? That's right. You think that the appearance of the lines that are non-visible, you think they disturb our vision, or is it something that the brain can just discard and still understand what's going on?
I would say it's not like completely brain can understand it, but when you divide it into the parts and like when you get into the depth of it, wireframes can be handy. It's not like easily understandable. Yeah.
Yeah. Well, let's just look at the buildings over there. Obviously, you can see every single line, so even the ones that are not visible. But it doesn't bother me much. Does it bother you?
No.
No. So the question is, if these wireframes obviously are not as intrusive, then why do you want to get rid of them?
We don't. It's like that's where the wireframe ambiguity comes into the place. We cannot exactly come into the conclusions just with the wireframe. It might seem one image to your eye when you see in like one angle, but it's not the complete art when it comes to the different angle. You might be facing this kind of problem with the wireframe. So that is what is our next topic about the wireframe ambiguity. So it refers like a situation where 3D modeling, where the wireframe representation of an object is not clear or subject to interpretation. It is sometimes difficult to determine indeed structure or shape. So the lack of clarity can result in potential misunderstandings and or inaccuracies during modeling of a design procedure. So even when you see a cube representation here, the vertices are plotted here. In this wireframe, we see the lines connecting the vertices, creating a cube. However, without additional context or labeling, it may be ambiguous which lines represent the front or back or faces of the cube. Just like that, when you go back to that picture, we never know which part, if the building is facing in the front or back. So those are some viewing misinterpretations we can face with a wireframe. And depth queuing. Depth queuing is one technique where you can overcome this wireframe ambiguity to some extent. So uncertainty can be eliminated with it in the wireframes to include the depth details when constructing a 3D scene. So there are several ways to include depth information. Like one is rendering distant objects at a lower intensity than the other ones, hence giving them the appearance of the depth. This technique is called depth queuing. So here we can see an image here, a wireframe object displayed with the depth queuing. So the brightness of the lines decreases from the front of the object to the back. So it can be viewed like representing this is the front and not confusing which is the back. So this is the depth we can use to overcome the ambiguity. And let's talk about the 3D viewing pipeline. So generating a computer graphics view in a 3D scene is similar to the process of involving taking a photograph, just like how we discussed in the first introduction. So we need to select a position, whatever, like whenever you take your phone and try to picture or take a photograph of something which is like a 3D object, or like everything is 3D in our view. And we need to select a position view to place the camera first. And we need to choose position where how the scene is being displayed. And then we need to fix the camera orientation. And finally, when everything is like everything seems to be perfect, and you click the capture button. Yeah. So let's talk about like 3D viewing pipeline modeling transformation to the viewport. So how does the process, each and every step we're going to discuss. So the first part is like the modeling coordinates. We take the modeling coordinates, which are like very basic, and we apply the modeling transformation, which makes them to convert them into the world coordinates. And then we apply the view transformation. Uh, we get the viewing coordinates from that point of view. And then the projection transformation is one technique where we can obtain the projection coordinates. Once we obtain the projection coordinates, we need to normalize them and applying the transformation. And then using the clipping technique, we can get into the normalized coordinates. Once everything comes to the normalized coordinates, and viewport transformation is applied to ultimately get the device coordinates. So this is the procedure what I have tried to explain here. When we try to illustrate, the viewing coordinate system defines the viewing parameters, including the position and orientation of the projection plane. The two-dimensional clipping.
You muted yourself.
Okay, are you able to hear me now again?
No, I can hear you.
Yeah, the projection operations are performed to convert the viewing coordinate description of the scene to coordinate positions on the projection plane. The clipping operations can be applied for all devised independent coordinate transformations from like world coordinates, normalized coordinates, just like we saw it in the image. Once they are completed, the final step is like viewport coordinates to device coordinates within a selected display window. So talking about the view coordinates in a 3D parameters, to establish like three-dimensional viewing reference frame, the following need to be done, like to position the world coordinates, p0 like x, y, and z for the viewing origin, which is called the viewing viewpoint or the viewing position. Specify a view of vector v, which defines the y view of the direction. For such like 3D space is required to assign the directions of one of the remaining two coordinate axes, which is typically combination with the second vector that defines the z view axis. So this is like a standard x, y, and z coordinates, and this is like an established three-dimensional view where we define the y view first, and use the other vectors to define the z and the x view. So here, right-handed viewing coordinate system is used with the axis here, and relative to the right-handed world coordinate frame. And so this is a view plane. When we discuss about the viewing direction, is usually towards the z view axis. Hence, the view plane is also called the projection plane, which is always like perpendicular to the z view axis. The orientation of the view plane as well as direction for the positive z axis can be defined with the view plane, normal vector with n. Here you can see the normal vector, which is projected towards the z view axis, and the orientation of view plane and normal vector can be seen here. And this is the UV and viewing coordinate reference frame with respect to the X, Y, and Z axis. The direction of the X view axis is like the view plane normal vector, and the direction of the Y view axis is up towards the V, and the direction of X view axis taking the vector cross product of V and the N to get the U. So here we can see how the U is obtained with the cross product here, V cross N by modulus of V cross N, and V is obtained n cross U. So here are the view Vx, Vy, and Vz view of the reference coordinate reference frame with respect to the X, Y, and Z axes. Yeah, so this is the clipping plane. Clipping plane is one technique are used in the 3D computer graphics in order to prevent the renderer from uh, calculating surfaces at an extreme distance from the viewer. The plane is always like perpendicular to the camera to set distance away and occupies the entire viewport. The two clipping planes determine like how much of scene is being seen by the camera in the viewport. So when you talk about the clipping plane to respect to the camera point of view, you can see a back clipping plane and the front clipping plane, just like in the image, and the gap in between is the viewing frustum. And yeah, so this arises like this generates multiple viewing effects based on the different camera angles or uh, what we can say different focal lengths of the camera. We can obtain like very varying different parameters. Fixing a view position is a direction of in the direction of the vector n is changed. We can visualize like object around viewing coordinate origin. Composite display made of multiple views from the fixed camera position can be applied on varying. So here are a few of the effects we get by varying the direction of the direction of the n. So one such is like wide angle view in 3D graphics refers to the view of a perspective that covers a larger field of view. We can see this wide angle camera view recently in all our cameras, in the mobile cameras. So when we need a picture very bigger than what a normal camera can picture. So to get more to get the more image into the picture, we use the wide angle camera. Here are the few examples we can see. Um, this is like a Times Square where you can see all. You can't just picture with a 2D getting all the image, all the like buildings and all. So when we use the camera like a wide angle, it changes a perspective to a different point, making a larger buildings to be available. And in the same way, there is also a wide angle camera effect called paranormal effect, which we are seeing lately. This is our Tampa Riverwalk view, where it is captured using the panoramic view, covering entire the landscape, like buildingscapes, the cityscapes. And so panning is another effect what we often see. So this is like a 3D modeling in a computer graphics. Like panning means moving parallel in the current view plane. In other words, it means like camera moves perpendicular to the direction it is pointed, and the direction does not even change. So even when you often see many movies as well, where they show the F1 races or a police being chased, or like a robber is being chased by the police. Even when they are moving in a very fast, the direction of the camera does not change, capturing the right moment. And yeah, this is like walk. This is like a walk around.
Yeah, the walk around just walked away.
Sorry,
Yeah, we are back.
Yeah, so this is a walk around view. This can be like in a daily point of view. Whenever you are walking, your surroundings, whatever you are able to see, just like imagine a cup is being placed just in front of you. You are sitting in front of it with a handle towards the right. But when a person sees it from the left, it just seems as a square or a rectangle in shape. This is like a effect being created in a walk around. The concept of walk around is like simple, like walking people around, looking at the things around in a particular scene. This effect allows us to walk around the object and view it from different sides, giving us a many perspectives. And yeah, when you place a camera, like a dash camera, in front of a car or a bicycle, you might be getting like a different view angles. Um, let's imagine a scene being captured, maybe a crash scene or something, where you are driving the car and your perspective is different, and the traffic camera will be captured in a different way. So these are the that's a simple example where different angles can be formed around just in your perspective. Yeah, that's all from my side, Professor.
Can you hear me, Professor?
Yes, loud and
Okay.
clear.
Can you see my screen?
Yes, I do.
Okay. So transforming from world viewing coordinates. So in the three-dimensional viewing pipeline, the first step after a scene has been constructed is to transfer object description to the viewing coordinates reference frame. The key concept here is we need to convert the coordinates of the object into the viewing coordinates. So yeah. So how can we do that? So we can accomplish this conversion using these methods. First step is to translate the viewing coordinate origin to the original of the world coordinate systems. Like the pictures on the left, we need to move the point P to the point P0, right? Move the viewing coordinate to the world coordinate. And the second step is apply rotation to align the X view, Y view, and the D view axis with the world XW, YW, and the DW axis respectively. So in the picture on the right, after moving the point, we need to rotate the vector. So we need to rotate the vector for black lights to the purple lights to match the vector of the world coordinate. Yeah. And so we assume that the viewing coordinate original is at world position P0, X0, Y0, D0, and T is a matrix for translating the viewing original to the world origin. And R is the rotation transformation matrix. It's used for the rotate the vectors. Yeah. And the N is the final transformation matrix is obtained by the product of the T matrix and the R matrix. And we can after that we can get the matrix elements like these three functions. Minus U part multiple P0 equals this one. Yeah. So after we get a matrix, we can multiply by the viewing coordinates, and then the conversion is complete. Yeah. And multiply the old coordinate, and we will get a new coordinate. So next. So I think here's a brief introduction for parallel projection and the perspective projection. Yeah. So parallel projection is achieved by projecting parallel projection lines onto a view plane, and the perspective projection is the projection lines is extending by convergence point onto the view plane. Yeah. So yeah, next. So orthogonal projections, a transformation of object description to a view plane along lines that are all parallel to the view plane. Normal vector n is called an orthogonal projection. And this produces a parallel projection transformations in which the projection lines are perpendicular to the view plane. And the front, side, and the rear orthogonal projections of an object are called elevations. A top orthogonal projection is called a plane view. So you can see in the figure 17, the view plane will get the one side of the object, and the top projection will call a plane view, and the front and the side will call elevation view. And also the distance between the view plane and the object will not affect the apparent size. So the size on the view plane is as same as the item surface. Yeah. So orthogonal projection coordinates with the projection direction parallel to the z-view axis. The transformation equation for an orthogonal projection are trivial. For any position xy in viewing coordinates will be a simple xy, xp equals x and yp equals y. So the z coordinate values for any projection transformation is preserved for using the feasibility determination procedures. So we still keep the z coordinate. We will not discard it. Next. So orthogonal projection field value. Last week we learned to set out a clip window for 2D viewing by selecting the 2D coordinates of its lower left and the upper right corners. And you can see the figure 20. The clip window is the area that we can see, you can watch. And for 3D viewing, the clip window is positioned on the view plane where it is edge parallel to the X view and the Y view axis. So if we only consider X view and the Y view axis, there will be a infinite view value. So that's a problem. So we need to limit the Z view coordinates. So these limits are used to form the top and bottom and the two sides of clipping region called the orthogonal projection field value. And these two planes are called the near-far clipping planes or the front-back clipping planes. And we get these two planes, so we will get a rectangular visible value like figure 22 is a regular rectangular visible value. And our view of the sense will then contain only those objects within the field value. With all parts of the things outside the field value will be eliminated by the clipping algorithms. So normalization transformation for an orthogonal projection. So we know that the orthogonal projection for any spatial points xy will be a simple xy. So thus once we have established the limit for the field value coordinate distribution inside this rectangular parallelopy are the projection coordinates, and they can be made into a normalized field value without any further projection processing. So some graphic packages use a unite cube for these normalized field values with each of the x, y, and the z coordinates normalized in the range from 0 to 1. Another normalization transformation approach is to use a symmetric cube with coordinates in the range from -1 to 1. The concept is more like scaling. And why we need to do the normalization. So the reason is that rather than derive a different projection matrix for each type of projection, we can convert all projections to orthogonal projections with the default field value. This strategy allows us to use standard transformations in the pipeline and the makes for efficient clipping. Yeah. And this example for normalization transformation. we will assign the position on x mini and the y mini and the d mini will be mapped to the normalized position -1, -1, -1, and the position x max, y max, and the d max will be mapped to the 1, 1, 1. Yeah. So it will like the figure 24. And the next is a transformation matrix from what coordinate to normalized orthogonal projection coordinates. And how can we get this matrix? So we two step move center to original and scale to have size of length 2. Why the length is 2? Because the max and the max is 1 and the mini is 2. The minimum is the -1. So 1 minus -1 equals 2. So the range is 2. So we will get this matrix, and we use this matrix to multiply the original coordinate, that we will get a projection coordinates. Yes. And
typically used in the computer graphics or the engineering or the technical drawing. So the main difference between the parallel projection and the perspective projection is the parallel projection will have a parallel lines like at infinite, like we assume that the center of projection at the infinite point, so that the parallel lines will remain constant in the 2D image as well. But in the perspective projection, we assume that the center of the origin will be in the finite section. So the converging point will be at the finite point, so that the parallel line will not remain same in the perspective projection. So the center of projection infinity will be result of the parallel projection. So it basically simplifies the realistic representation of the appearance of the object. It simplifies the it is also simplifies the projection process and ensures that object do not converge towards a vanishing point. So here we can see that we have a parallel line, we have the parallel lines, so that it is not be converged at any point in the when the user is visible to the object. So I'm explaining, so also the as process of this, we are talking about the classification of projections. So
can we put this in a projection mode or presentation mode, so we get rid of those, makes it nicer, more readable? Put it in presentation mode, please.
Okay, I'm sorry, sir.
Right there.
Yeah,
see,
I'm sorry.
Much better. Now we can see much better.
I'm sorry, I just forgot to put the presentation. Okay, is it clear, Professor? So in the classification of in the classification of projection is mainly depend upon the center of projection. So as I said that if the classification of the center of the projection is an infinity level, it will be lead to the parallel projection. If the center of the projection is a point where we can see, it will lead to the perspective. So it is also have a converging point. So at the it doesn't lead to the same size to the object when we convert to the when we convert to the 2D projection in the perspective. But in the parallel projection, we doesn't have any converge. The results will maintain the size regardless of the distance on the viewer. So it is one of the main difference between the projection of the parallel projection and the perspective projection. The orthogonal projection is a type of projection where we have a perpendicular to the plane. I'm sorry about this, sir. So if the projection of lines are not perpendicular to the projection planes, it is called oblique projection. So we can see, here we can see the perspective and orthographic and oblique projection. So as I explained here, we have a center of projection. So this line is perpendicular to the projection plane, but in the oblique projection, we doesn't have a perpendicular to the object, like the projection lines is not perpendicular to the projection plane. So the main difference we can see in the picture, the perspective and the oblique. So we have a point here, and so it is 90 degree between the projection plane and the projection lines. But other than 90 degrees, we can observe all other angles in the oblique. So the graphical projection is mainly divided into parallel and the perspective. So as I said, the parallel is also again divided into the two types, the orthographic and the oblique. So in the orthographic, the projection of lines will be the parallel to the projection of planes. So that can be three categories: isometric, diametric, and trimetric. In the oblique, we doesn't have a 90 degrees between the projection of line and the projection of planes. So it can be divided into the cabinet, cavalier, and the military. So we also have a perspective 1D, 2D, 3D. So I'm explaining about the oblique projections. So the oblique projection is not normal to the projection of planes, though here the strike of projection planes will be in an angle other than any 90 degrees, because as I said, it is not perpendicular to the projection of plane. So we can see a better view when we are seeing from the oblique projection. The view we are also have a better compared to the orthographic, because orthographic projection has a limited view for the viewer, but in the it is mainly used in the purpose of the pictorial purposes, like rather than the formal and the working drawings. So it will also allow the additional shearing. So the here in the oblique projection, the two coordinate axis doesn't change the mapping, but the one thing is will be going to change the coordinate axis. So here three will be represented by the alpha, beta, and the gamma. So I'm more explaining about this in the further slides. So it is a general representation of the oblique projection. We have a 4 matrices here. So it will represent in the translation, skewing, and the when we are transferring to the 3D to 2D. So it is a mathematical representation of the general oblique projection. I'm explaining the types of the oblique projection. So basically it will be divided into two projections. It is a caveat projection and the cabinet projection. So in the caveat projection, the size will be not reduced. It will remain same as the 3D to 2D. But in the cabinet projection, when we are converting this, the size is reduced into half. So basically we call as a cavalier and the cabinet projection. The cavalier projection is will maintain the 45 degrees angle between the projection and the projection planes. Like when we are converting to 3D and 2D, the projection line which is perpendicular in the 3D will remain the same length as in the 2D as well. It will doesn't change any length when we are converting the 3D to 2D. So we have a 3 axis in the 3D image. It is X, Y, and Z. So we are not for shutting the all three. Here we are for starting factors for all three directions are equal. It doesn't affect one axis more and other axis less. So it is categories. I'm sorry. 1 minute, Professor. So it is categories as an isometric projection. It means the size will be reduced in same in all three equal in all three directions. We equally reducing the size in all three axes. So that's why it is called isometric projection. So it is the representation of the cavalier projection in the matrix form. So here we are putting the beta equals to 45 degrees. So it is called cavalier projection. So here when we are converting the 3D to 2D, it simplifies the projection process. The main usage of cavalier projection is in the technical and engineering drawings, because it will give the accurate representation and measurements are essential. So where we can use it, like applications is like architecture, mechanical drawing, and civil engineering. So it will give the clear visualizations for the dimensions, because when we drawing anything in the architecture, the dimension is very important. So it will give the clear representations to the architects to use this type of projection, so that they can get a clear view to explain their clients or the to clients to someone, because it will be main using the blueprints. So the concept of blueprints to get an accurate picture of the drawing, the particular drawing. So the blueprints will be used in the cavalier projection will be used in the blueprints, because it is a representation of the future outcome of the drawing. It may be building, it may be like something like car, it will be maybe any device. So it will the blueprint is a representation of the original thing. So it doesn't accurate, maybe it doesn't share about the object sizes and shapes, but it doesn't give any depth perception, because we have a limitation for the Cavalier projection. Because of that, we doesn't have a depth perception clearly in the Cavalier projection. Other type is cabinet projection. So it is very similar to the Cavalier projection. The cabinet projection is very similar to that. So here we are changing the projection plane from 45 degrees to 63.4. So here the beta is 63.4 degrees. As I mentioned earlier, the depth will be changed. The size will be reduced into off scale. In the previous Cavalier projection, the depth will be the same, the off scale itself. But here the depth will be changed, the view will be changed to the viewer. So rather than putting the projection plane in the 45 degrees, we are putting it in 63.4. So in the Cavalier projection, we are foreshadowing the all three axes equally, but in the cabinet projection, we are not foreshadowing all three axes equally. We are only foreshadowing the only one axis, that is Z axis. Remaining all other axes will be remain the same. So in the cabinet projection, as I said, the only main difference is there are the two main differences. The size is reduced into half, and the beta angle is changed to the 63.4. So the application will be the more same for the Cavalier and the cabinet projection. It is also used for the architecture and the blueprints. When we want the limited view, the cabinet view will be used because it will give only the one side of the view. I'll show a picture, Professor. So this is a Cavalier and this is a cabinet. So in the Cavalier view, the user can assume the 3D picture in some way, but in the cabinet, we can only see the exact front side view. This is the main difference. We are getting three axes here because we are foreshadowing the three axes equally. But in the cabinet, we are not doing that. We are only doing the only one cabinet, so that the main difference between the Cavalier and the cabinet section will be like this. The next
which one? Let's go back. Which one is it more appealing to your eyes?
So if I want more, if I want to see the image more, I prefer to go Cavalier. But if I want only one side view, only one picture representation, I'll go for the cabinet. So basically, maybe it depends upon the situation, Professor. If I want only front side view, I will prefer cabinet rather than the Cavalier. But if I also want to see some extent beyond that, I will see the Cavalier. So sometimes it depends upon the situation what we need to choose.
Okay. Continue.
So the next is the view volume. So when we are converting from the 3D to 2D image, so the clipping planes, so we need to convert the clipping planes from 3D to 2D. So as part of this, we have one picture will have a left, right, top, bottom, front, all views on that. So when we as we discussed in the parallel projection, we discussed about the only three views, but when we want to change something from 3D to 2D, we need to consider every side. It may be like left, right, top, bottom. So in order to converting 3D to 2D, we need to cut. We need to short some areas to get focused picture on the paper. So these are the images which I provided to conversion of the 3D rendering to the 2D. This is the oblique. So as I said, oblique will be the perpendicular to the projection of plane. So that's why we are getting the view like this, Professor. So it is some of the mathematical representations of the projections. So here we are viewing the reference point and the viewing factor. So depend upon the viewing factor also, the view volume will be changed according to the viewer. So in order to cut the remove objects, that is extend beyond the fall outside, define the value. Because in order to obtain the 2D image, we need to cut the excess part outside the volume, which is we need only one side view for the volume. So it will be changed from the 3D to 2D. This is some of the mathematical representations of the converting a view volume from one side to other side. So this is as Darshan said, that this is the transformation of the oblique projection. I don't want to explain again the same thing. So it is a main key chart to and the process to converting the modeling coordinates to the device coordinates. It involves some steps. Modeling coordinate and modeling transformation will change the word coordinate. So viewing transformation again change to the view coordinate. So the project transformation will result to the normalization, transformation, and the clipping. So this is the one of the crucial part to change the 3D to 2D. So it will also be the viewport transformation. At the end, we'll get the device coordinates to obtain the 2D image in the picture. So we'll assume that X, Y, Z are the three-dimensional axis, and we'll get the two X, Y, and axis. When we as my teammate said before, we'll convert -1, -1, -1 to 1, 1, 1 to get that picture in the image. So there's a normalized volume for the parallel projection, professor. So basically normalized view volume will be assume that rectangular or the cube box. So we assume that origin will be 0, 0, 0. It can be maybe cube, it may be or rectangle. So we are assuming that origin will be at 0, 0, 0. So the normalized views serves as a purpose of the reference space where objects are placed in the before projection. So it transforms the position relative to the normalized view volume. So modeling transformations, as I explained in the chat, modeling transformation are applied to the position and as well as the orient objects with the reference cube. So objects within the normalized view are projected directly to the projection plane without any perspective distortion. As I said, we doesn't have any center of projection in the finite section. We assume that the projection of planes will be the parallel. It will remain same in the 2D image as well. So we are just moving the coordinates in order to get the 2D coordinates from the 3D coordinates. So this is the we are converting 3D space to 2D space. So it is the mathematical representation of the normalized view volume for the parallel projection. Upper right corner to the lower right corner, we are changing -1 to 1 along the x and y axis. So we also call normalized device coordinate as NDC. After projection, we'll get NDC for the 2D image, so that we can form the image as well on the picture. So we in the process of clipping or in the process of normalized view volumes, we'll get the rotation, skewing. After all this, we'll get the 2D representation, and by removing the excess part from the 3D image to 2D from the 2D. So in order to get that, it sometimes according to the viewer needs, we'll choose the caviar or the cabinet projections. So it is one of the key role to project by projecting the 2D to 3D to 2D. So if the user doesn't want to change any shape or any size, the user will select the cavalier or the cabinet. It doesn't change any size toward the conversation, but in the cabinet we'll get the scale by, we'll reduce the size by half.
So 3D viewing projections and perspective. So I'm Manish, and I will be explaining about team. I'm from Team Hamilton, and I will be explaining about the perspective topic here. So perspective projection or perspective transformation is a non-linear projection where three-dimensional objects are projected on a picture plane. This has the effect that distant object appears smaller than the nearer objects. This means if you're trying to capture an image from a camera, so you're trying to capture a 3D image onto a 2D picture or a 2D image. So this is all about the perspective where you capture the elements of the 3D and you convert or you transform that and put it as a 2D image. So also one example is when you have parallel lines in your image, as noted from the image below, you can see that it appears that they coincide or they merge somewhere at the end, but it is not true, because we know the railroad tracks, they don't merge, so it appears to be merging at some point infinity. The point where it appears to be merging or where the point is lost, it's called the vanishing point. And the right way to understand about this perspective is think about the same example of where you capture the 3D image, and when you look at the people or the objects through the viewfinder in your camera. So that is about the perspective here, and also there is also a mathematical formula to actually transform the 3D objects into a 2D so that it can be put on a 2D plane. So for that we require the camera position, orientation, and field of view and control. These are all required for that, and the formula is like this. Yeah, so here this is a sample projection where how the different points are projected on the plane, and this is actually the matrix transformation formula which transforms a 3D object into the 2D onto a 2D plane. So here the terms which are needed are like a, x, y, z, which means that the point that you want to be projecting, or the object of some point that you want to be projected on c, x, y, x, comma, y, comma, z is the point representing the camera, and theta is the orientation. E, x, y, z is the display surface position, which is with respect to the camera pinhole C. So to actually find the distance, or to represent it, we have a vector d. So what that is represented as dx, dy, and dz in the as shown in the formula below. So this matrix is essentially, it's nothing, just subtracting c from a and applying a rotation of negative theta to the result. So this is called the camera transform, and this is the formula for that. And there is also one more vector formula to it, which we'll see in the next slide, which is this. We can see that we can also do this, we can also get the same values without using the matrices. Also, cy in this formula, the cy denotes cos y and sy denotes sin y, and it's the same with the other axis. And there are different types of perspectives here. One is like one point perspective. One point perspective projection occurs when any of the principal axis interacts with the projection plane, or we can say when projection plane is perpendicular to the axis. So we can see like x and y axis, when they're coinciding on the projections of x and y axis, they're coinciding on the z axis, that where the vanishing point is there. So that's one point perspective where there is only one vanishing point, and it is only perpendicular to the x and y axis. So there is second kind of perspective, which is the 2-point perspective. This appears when the projection plane crosses the two main axes, that's when actually the 2-point projection occurs. In the above figure, we can see that like projection plane is actually interacting with x and y axis, whereas z axis remain parallel to the projection plane. So here there are two vanishing points as shown in the image. Here there are three vanishing points when all the three axes cross projection plane. 3-point projection occurs. Like no major axis exists that is parallel to the projection plane. So here this has the three vanishing points. So the 3D space is actually defined by three axes, which is the vectors x, y, and z. These three axes create an axis system. All points of the 3D space and can be expressed as a linear combination of the vectors, or you can call the dot product, or the scalar multiplication of the scale. The small x is a scalar, the lowercase x is scalar, and capital X is the vector. So when you do the dot product, then you'll get like the volume of the entire 3D space is infinity. The viewing volume is actually the amount of the space that delimits the 3D space by creating a closed volume. Points outside this volume will not appear on the screen. This particularly explains the first G-translate, which is a method. The viewing volume actually has two kinds of projection: perspective projection and the orthographic projection. Perspective can be thought of like the perspective projection changes with the viewing distance from the observer, or it's like, for example, when you see a car from farther distance, you know the car looks smaller because the amount of distance between the car and you has increased. It's just that also the viewing volume, I mean the amount of car that you see in your vision or in your field of view is smaller. So that is perspective projection, which changes with the distance. Orthographic projection is just opposite to that, where the render does not get affected by the distance. For example, like a text on a screen or a 2D object. Also, perspective projection, with this kind of projection, the viewing volume shape is truncated pyramid. So, for example, when you see the image on the left, can see that you can see the near and far. The viewing volume for the image on the left is actually the image on the right, where you can see the X and Y and Z axis. Here, the 3D viewing projections. Here, this is the orthogonal projection where it is actually parallel piped. I mean, it does not get changed with the distance. Also, for the clipping ready transformation, the Z values of the Z values of spatial positions, they actually remain constant. We have an orthogonal projection if VPX and VPY are 0, and matrix M oblique is reduced to the identity matrix. So that's why when if EPY and VPX and VPY are 0, the matrix M oblique will be reduced to the identity matrix. The matrix represents as a Z-axis sharing transformation for a generic oblique parallel projection. This effect is like near to the oblique view volume into a rectangle parallel piped, as illustrated below. Thus, positions inside this view volume are shared into orthogonal projections coordinated by the oblique parallel projection transformation. The formula is given by the image on the right side, where all the elements along the diagonal are 1 and all the elements below the diagonal are 0, and the other formulas is like negative VPXY, VPIY, the division formula. And also, we need to normalize the view before actually proceeding with the clipping. So because the oblique parallel projection equations convert object descriptions to orthogonal coordinate positions, we can use the normalization process that follows this transformation. The oblique view volume has been transformed into a rectangular parallel pipe as explained in the previous slide. We map this to the symmetric normalized cube with a left-handed coordinate frame using the same normalization as in orthogonal. The transformation of this M oblique requires conversion from like scene description to orthogonal projection coordinates and transformation M ortho norm is ortho norm matrix is previously referred, which maps the contents of this orthogonal view into symmetric normalized view. So the formula for this oblique parallel projection is matrix oblique normalization is nothing but matrix ortho normalization times matrix oblique. So this is what actually the actual normalization would look like. And thank you.
The 3D clipping can be defined as it's a method to selectively enable or disable rendering operations within a defined region of interest. So clipping is before projecting, we need to eliminate the portion of the scene that is outside the viewing frustum. So basically it's a process used to determine which parts of the 3D dimensional scene should be rendered on a 2-dimensional screen or a viewport. So it is an important step in rendering pipeline of 3D graphics. Because it helps us to ensure that only objects of the portions of objects that are visible within the viewing frustums are drawn on the screen. So next, 3D clipping is also just like a 2D clipping, and this can be achieved by 2 steps. That is by discarding the objects that are behind the camera or outside the field, and only clips that objects that intersect with any clipping plane. So the image shows that the plane is near the camera or the eyesight that is far clipping plane, and discarding the objects outside and behind the planes, and only considering the object that lies in between the near and far plane, and even half of the object lies between 2 planes, and it will render, and these are discarded. So 3D clipping, this can be achieved in 2 basic steps. As I earlier said, discarding object that cannot be viewed, clip objects that intersect with any clipping plane. So this is one of the example. And coming to 3D clipping algorithm, so by using 3D clipping algorithms or normalized borders, the weaving pipeline and clipping procedures can be done in very effective manner. So before executing the clipping routines, all device independent transformations are concatenated and applied, and each of the clipping boundaries for the normalized view volume is a plane parallel to one of the Cartesian planes, regardless of the projection type and the original shape of the view volume. 3D clipping, in 3D clipping, normalization strategy basically makes the clipping very efficient. So that's the reason we use normalization here. Depending on the normalized view, volume being a unit cube or symmetric cube with edge length of 2, then the coordinate positions can be at either 0 or 1 or at -1 and 1. For the symmetric cube, the equations for the 3-dimensional clipping planes are as below. the x coordinate will be -1 and the x of max coordinate will be the 1. So y of min coordinate will be the -1. Similarly, max will be 1, and similarly the z minimum will be the -1 and the max will be 1. So 3D clipping algorithms, like the x and z y clipping borders, as earlier stated, are the clipping windows normalized limits. Those are the limits, and z clipping boundaries are the near and far clipping planes normalized positions. For three-dimensional viewing, clipping algorithms locate and preserve all object portion within the normalized view volume for display on the output device. The algorithms, these 3D clipping algorithms are extension of the two-dimensional methods, and using the normalized boundary planes of the view volume instead of the straight line boundary of the normalized clipping window. So when we have a different objects, all parts of the objects that are outside the view volume clipping planes are eliminated totally. And coming to the use of homogeneous coordinates in the 3D clipping, the homogeneous coordinates has a parameter h, and that is set to the 1. The homogeneous coordinates corresponds to the Cartesian projection coordinates. This is frequently the case with the parallel projection transformation. Like the parallel projection is similar to the homogeneous coordinates with the Cartesian project coordinates. A perspective projection, on the other hand, generates a homogeneous parameter that is a function of the z coordinate for any geographical position. The homogeneous parameter can be a positive or negative, and if the clipping is performed, the projection coordinates after division by the homogeneous parameter h, the information can be lost and the objects may not be clipped properly. So if the objects are not clipped properly, the effective way to handle with all possible projection transformation and object representation is to apply the clipping routines method to the homogeneous coordinates representation of spatial positions. Then coming to computer graphic libraries process spatial positions as 4-dimensional homogeneous coordinates so that all transformations can be represented as 4x4 matrix. So as shown here, there are it is a 4x4 matrix where x coordinates, x, y, z coordinates are there, and h parameter, which is a homogeneous coordinate, that is set to the 1. So after a position has been passed through the geometric weaving and projection transformation, it is now in the homogeneous form as shown here. So where matrix M represents the concatenation of various transformations from coordinates to the normalized homogeneous projection coordinates, and the homogeneous projection H may no longer have the value 1. So coming to the line and plane intersections, a clipping plane can be specified with the plane parameters A, B, C, D. The plane then divides 3-dimensional space into 2 parts so that all parts of a scene that lie on one side of the plane are clipped off. So we can see that the plane is intersected with the line, but that is in the 3D clipping part, so that we have to eliminate or we have to clip a line segment. So this image shows this is an example for a clipping a line segment from an intersection of the line and plane. So it's a clipping line segment against the plane with a normal vector n. Assuming that the objects behind the plane are to be clipped, then any spatial positions x, y, z that satisfy the following inequality eliminate from the scene. So